Okay, so there's number 33 on the homework. Um, so, right, it says, I didn't write the instructions, but we have to find, if U1 is a vertex in G1, then I would like the degree of U1 in the graph G1 union G2. This plus means union. So if you, and I encourage you to take a look at the book at what the definition of this graph operation is. But what this is basically drawing this graph basically amounts to drawing the graph G1, and then somewhere off to the side, I'll just draw a graph G2, and I don't draw any extra edges between them or anything like that. I just draw a copy of G1 and a copy of G2 right next to it, basically. So a graph in G1, the neighbors that it has in this graph are just whatever neighbors that it had in G1. So the degree in the new graph, G1 plus G2, is the same as the degree was in G1. So that's part A. In part B, we're talking about the join instead of the union. And what you do for the join is you draw a copy of G1, and then you draw a copy of G2. Actually, maybe I have some room over here. It's like you copy G1, you copy G2, and within this bubble, it looks exactly like G1, and within this bubble, it looks exactly like G2. But then what you do is you draw every possible edge, and I'm just going to scribble, but this scribbling represents every possible edge from a vertex on this side to a vertex on that side. So what is the degree of U1 going to be? Say if U1 is some vertex in here, then let's count its neighbors. So first of all, it has some neighbors in this bubble. It has whatever the neighbors that it had in the original graph G1. So that's this many. But also it has neighbors over here. How many? Well, all of them. U1 is adjacent to all of these vertices. And how many of these are there? There's N2, because in the instructions it said the order of G2 is N2. Okay. Part C is about the degree of this vertex in the product graph. So remember, the product graph G1 with G2 has vertices that look like this. It's an ordered pair, and the first entry of the ordered pair is the name of a vertex in G1, and the second entry is the name of a vertex in G2. So this ordered pair is a vertex in G1 times G2, the product graph. And I want to talk about its degree. So I particularly encourage you to look in the book at the definition of the product graph. And in particular, how do you decide what are the edges of the product graph? I'm going to kind of go through it, but I encourage you to read that first. Well, this vertex is adjacent to basically two types of vertices. It could have the same entry in the second slot, and the first slot could just be something that's adjacent to U1 in G1. So in other words, this vertex is adjacent to any vertex like this, as long as the second slot has the same thing, and the first slot is a neighbor of this one. So V is just adjacent to U1 in G1. How many vertices like this would there be? Well, it's really just how many choices we would have for V, and we know that V just has to be adjacent to U1 and G1, and so the number of vertices V that are like that is the degree of U1 in the graph G1. So there's that many like that. And then there's another type of vertex that is adjacent in the product graph. And it's kind of, I don't know, like a mirror image of the first type. The first type was when you keep this coordinate the same, and this one just has to be a neighbor of this one. The second type is going to be switched. We're going to keep the same first entry, and the second entry just has to be a neighbor of u2. So it looks like this, and w is a neighbor of u2 and g2. And so how many vertices w like that would there be? Well, it's the degree of u2 in the graph g2. So when we put these together, it was adjacent to this many vertices of this type and this many vertices of this type. So I add those two answers together, and that's the degree of this vertex in the product graph. Okay. Then there was just this last problem, which is kind of similar to the one we just did, except now instead of talking about the degree of a particular vertex in the union and the join and the product, we're going to talk about the total number of edges in the union and the join and the product. So the first two are not too bad. In the union, remember the union is just where you draw a copy of the first graph and then a copy of the second graph, and they're basically not touching each other. They're not interacting. So if G1 has M1 edges and G2 has M2 edges, then the number of edges is just going to be M1 plus M2. Then in part B, we're doing the join, which, remember, in the join, it's like this. You draw a copy of G1, a copy of G2, and then you draw every possible edge here. And basically, if I have M1 edges here and M2 edges here, then I've got M1 plus M2 plus, okay, how many like this are there? Well, I have every possible edge from a vertex in here to a vertex in here, and there's n1 vertices here and n2 vertices here, so the number of edges going across would be n1 times n2. So that's that. Okay, last part, and I warned you that this one is slightly hard. It's not impossible, but don't feel too bad if you struggled with this one. There's a number of ways to go about this, and so here's the way that I chose. I would like to base this off of what we did in the last problem, part C of the last problem. We found the degree of a particular vertex in the product graph. Because we have a way of talking about the degrees of vertices and relating that to the number of edges in the whole graph. In particular, we have the handshake lemma, which is if I add up all the degrees of all the vertices, then I get 2 times the number of edges. So if I already have some information about the degrees of vertices in the product, then maybe I can use that to figure out the total number of edges. So here I go. In any graph, the degree sum is 2 times the number of edges. So if I want to figure out the number of edges, I can always just do half the degree sum. So that's what I'm going to do. I put a half, and then this, sorry for the way this looks, this is a giant sigma for a sum. I had a kind of a lot to write underneath the sigma. I'm doing the degree sum, and I'm doing the degree sum in the product graph. So what I want to put down here is I want to sum over all of the vertices in the product graph. And the vertices in the product graph look like this, that they have names, that the names are ordered pairs. The first entry is a vertex in G1, the second entry is a vertex in G2. So what this says down here is really just I'm adding up all of the vertices in the product graph. And what am I adding up? I'm adding up their degrees. So this is exactly what I said I'm going to do. This is 1/2 the sum of all the degrees of all the vertices in the product graph. So how am I going to do this? So first of all, so the half just came right down. I can write this sum a different way. This sum is over all ordered pairs where u1 is a vertex in G1 and u2 is a vertex in G2. I can write this as a double sum where I'm doing the sum over all u1 that are vertices in G1 and u2 that are vertices in G2. This represents the same thing. Up here I have a term for every possible combination of a vertex in G1 and a vertex in G2, and down here I have the same thing. I have a term for every possible combination of u1 being a vertex in G1 and u2 being a vertex in G2. So this is just another way of writing the sum. And then I replaced this with this, because that's what we figured out in the last problem. We figured out that the degree of a particular vertex in the product graph was just the degree of u1 in G1 plus the degree of u2 in G2. So that's all I did. And now we have to add this up. So there's now two things in this sum, so I'm going to split them up. So I put a big set of brackets, and now I'm doing a double sum, and this is a double sum. It says the same stuff as here, so it's a sum of all u1 in G1 and u2 in G2, and I just put this here. And then separately, I'm doing the double sum of all of these, so I put this here. Okay, now in this one, notice this term doesn't depend on u2. It only depends on u1, meaning if I'm looking at this sum, I'm just underlining the inner sum, because in a double sum, there's like the outer sum and the inner sum. Since this doesn't depend on u2, if I'm doing this inner sum, it's just adding the same number over and over again. So how many terms are there in the first sum? There's a term for every vertex in G2. And how many vertices are there? There's n2 of them. So this sum is just adding the same number over and over again this many times. And so if I add that up, I'm going to get this much times this same number. Over here, I would also like to figure out what is the inner sum. I can't say the same thing as I said last time, because this is a sum, the inner sum is summing over u2's, and the term does depend on u2. But that's okay. I know what this sum is anyway. If I look at this inner sum, this is actually the sum of all the vertices, of the degrees of vertices in G2. I'm summing over all the vertices in G2, and what I'm adding up is their degree. In other words, this, by the handshaking lemma, is 2 times the number of edges in G2. So it's this. Okay, so we're here. And now we don't have any double sums anymore. I've just got this sum and this sum. Okay, so once again, I've got this one. In this one, N2 is like a constant that can pull outside because N2 doesn't depend on U1. It's this part depends on U1, but N2 doesn't. It's just like a constant. So this N2, I can imagine pulling this out to the front. And then what I'm doing is I'm just adding up the degree in G1 of U1. And we know what that is. This is the sum of all the vertices in G1 of their degrees. So this is the degree sum. If I do the sum of all the degrees in G1, I get 2 times the number of edges in G1. In other words, I get this. So that's this. And then what happens with this part? Well, with this part, actually nothing inside of here depends on U1 at all. So this is another sum where I'm just adding the same number over and over again. The number that I'm adding is 2 times M2, and I'm adding 2M2 plus 2M2 plus 2M2. How many times am I doing it? Well, I'm doing it once for every vertex in G1. In other words, I'm doing it this many times. So I've got 2M2 plus 2M2 plus 2M2 this many times, and that adds up to this. In the end, the half cancels the 2's, and I get this, N2M1 plus N1M2. A nice kind of symmetric looking answer after all of that ugly work.